All right, good morning. Really glad to be here today. Thanks to CDI and Daniel, all the folks for having me here. As you mentioned, my name is Ashley Llorens. I'm the chief of the Intelligence Systems Center at Johns Hopkins University. This is a relatively recent construct for us. So I'm going to talk about, I think it was a perfect ordering of the talks today. We heard a great talk from Greg on a lot of the innovation that's happening in the commercial sector, that's happening in academia around machine learning, around AI. At Johns Hopkins APL, we are a university-affiliated research center, so we support the government in building systems for defense, intelligence, national security, also space exploration and health. And so our challenge is really to leverage these tools to build systems that can help the government and help society with these critical challenges. So, you saw Greg's diagram about machine learning, robotics, and AI. And our work at Hopkins APL is really right in the center of that, bringing those disciplines together. And I'm going to tell you about some of the work we're doing in that area today. Okay, so this is just a smattering of the work we're doing. I mentioned defense, intelligence, health, and space exploration. So we actually have 12 mission areas at APL. We're pretty big. Johns Hopkins University proper, the teaching institution, is in Baltimore. We're in Laurel, Maryland. There are 6,000 of us, engineers and scientists, working across these different mission areas, again, trying to make critical contributions to critical challenges. Up in the right-hand corner there, in the red box, is a little robot called Ferdinand that some Hopkins professors back in the 60s created. And it was a real innovation at that time. It was an autonomous robot that would roam around the Hopkins APL hallways. It could autonomously find outlets to plug itself in and avoid people. And the reason I like to bring that up to start is the contrast between the novelty of that innovation at that time, that era, and the real enabling technologies, the fundamental enabling technologies that intelligence systems represent to our mission space today. Just a couple of examples. So in our national health sector, for example, we've created a system called Essence, which does population level disease monitoring. That was implemented in the state of Maryland after 9/11. And it takes features like absenteeism from schools and prescription medicines at drugstores and tries to predict the outbreaks of influenza and other disease. In the intervening time, it's now deployed across 12 states. So as Greg says, this is these kinds of intelligence systems are the technologies of today. There's a picture there of a doctor holding a drone. You've heard about drones doing drug deliveries. We're working on some of those things in Kenya to help deliver blood for things like HIV testing using drones, where the roads are really impassable, and a lot of times by the time the samples have made the long trek, they're not usable anymore. These are the kinds of systems we're helping to build today. All right, so you saw some of these examples in the great report that CDI has provided. And I'd like to try to set our work in the landscape of what's happening out there in the commercial world and in academia. So up on the top left, that's a Tesla factory. Wonderful innovation, exquisite control systems in these robotic arms. They don't have to be very smart, right? They keep doing repeatable tasks. So great example of robotics, not necessarily an example of AI. In the middle, you've got an Amazon fulfillment center where the robots bring the shelves to the people, keep them having to walk across the floor. Really an example of automation, a little more autonomy in the robots. Notice that the state of play there is such that we can't automatically do the picking off the shelves, which is where all the uncertainty is, right? And then the very impressive engineering feat, we've got Google pushing forward on the driverless car. I can't wait to get one when that technology catches up. Maybe I'll settle for an Uber at this point up in Pittsburgh. But you still got kind of a lot going for you there. You've got high resolution maps of the road. You don't have necessarily, other than in the urban setting, people trying to interfere with your satellite communications and things like that. To get where the Department of Defense and our other sponsors have really said they want to go, which is machines with greater autonomy, able to make critical choices and perform high-stakes tasks in the face of uncertainty. Our challenge is really to leverage all these innovations that you see on the top and build on that so we can have machines that are more autonomous and make for better, effective human-machine teams in these kind of critical tasks. Okay, so this is a little bit of the how do we get there. But first, what do I mean by autonomy? Because that's another term that kind of gets conflated. A lot of times we talk about autonomy as a particular technology. The way we think about autonomy, or the way we've been kind of helping the government think about autonomy, is that autonomy is the delegation to an agent to make a decision or to decide how they do something within some box, within some limitations. So that's the notion of autonomy that we're presenting here. And that's consistent with the one recently put forward by the Defense Science Board study on autonomy, which myself and several of us at APL were involved in. So I reference it on the bottom there. It's up on the DSB, Defense Science Board's website. I'd recommend that's good reading. So what do we need to get there? This notion of better, more effective human-machine teams, machines that can perform with greater autonomy in the context of those teams, right? We need smarter machines, and by that, we think about machine intelligence in three ways. So one is perception, so machines that are able to perceive and reason about their environment, control, so control systems, and then coordination, so machines that are autonomously able to collaborate amongst each other to perform complicated tasks. So we need smarter machines that act as better teammates. When we think about this notion of better teammates, we think a lot about the interfaces and the fluid kind of flow of tasks and control between humans and machines. We talk about command of machine teams, and when I command a machine team, I'm going to tell it what to do, but I'm not necessarily going to tell it how to do it. We are beginning to work with the Department of Energy, for example, on sending robots in to decommission sites so people don't have to go in there. This is a billion-dollar enterprise that they're trying to decommission some of these radiation-filled sites, and we're trying to help them understand how to leverage robots to do that. So we need these interfaces that move from command, tell the robot team what to do, not how to do it, to control. Maybe the team is smart enough to ask you questions when it needs help with the how of how to actually do it. And then finally, trusted autonomy. And so APL's got a breadth of work and disciplines. Not only are we thinking about the technology, we're also thinking about the analysis, the policy, the test and evaluations. And one of the most fundamental challenges with the driverless car example, for example, is the test and evaluation challenge, the certification challenge. And so we're thinking about all these things, and our place in the world is right in the center of those three bubbles, figuring out how to make systems that can perform greater autonomy in the context of human-machine teams to tackle critical challenges. I'll just say a word about the Intelligent Systems Center at APL. This is about 100-person research shop where we've brought disciplines together in machine learning, in AI, in robotics, and also in neuroscience to try to tackle some of these challenges and to create innovations. We're looking at greater collaboration among those disciplines across our mission areas at APL. So 12 mission areas, 6,000 people, just collaborating internally along these lines is difficult. And also looking to collaborate externally, so we're forming relationships now with industry and academia to try to tackle some of these challenges together. Okay, so Greg talked about the Go challenge, and I did a little bit of research just to understand in a little more detail why this was so impressive with Go. Right, so you've got this notion of a branching factor in computer science, which, if you think about the context of the game, is given the state of the board, on average, how many different things can you do on your next move, right? And so the branching factor for chess is about 25. The branching factor for Go is about an order of magnitude more than that. And so because of that, it's been thought of as a game of human intuition, because you can't really effectively enumerate all the possibilities of what's going to happen. We recently created a variant of chess at APL called reconnaissance blind multi-chess that better mimics some of the challenges that our sponsors have in their applications. And the notion here is that it incorporates an aspect of decision-making under uncertainty. The idea is, in reality, you don't know what the state of the board is. And so in this variant of chess, you actually have to sense and move. And so after the first move, you don't know what the state of the board is anymore. You have to sense a part of it, which is revealed to you. Take a move, your opponent senses, and then moves. And we're still actually trying to do the analysis to figure out what the branching factor might be for something like that. But this just gets to those really critical challenges where you'd like to have machines make decisions where they're in the face of uncertainty. So I'm going to ask if you could start that video. So you may have heard of the DARPA Robotics Challenge. We did not compete in that challenge, but DARPA asked us to come down and demonstrate some of our work in robot teams. So this is an example of what we call a marsupial robot team, which is almost, if you've seen those Russian Matryoshka dolls, you've got a series of robots with different capabilities that can sort of carry each other. So in this case, this is, again, this happened back 2015, part of the DARPA Robotics Challenge. It was a demonstration. This is a case where a robot team, the idea here is that the robot team is autonomously investigating a chemical spill in this container. And so we've got Robo-Sally, this anthropomorphic humanoid platform with these two arms, highly dexterous arms that we created for DARPA. And so she can open the door, but she can't get in. She launches the UAV off her back. The UAV can get in, but can't get under the containers. The little ground platform there, which is one that we developed at APL, can get under the containers, right? So this was sort of, I'll say, a semi-autonomous demonstration of where we'd like to go. Some of the thinking, or all of the thinking as to which robot would do which task was done ahead of time by the engineers. Robo-Sally acted autonomously, UAV acted autonomously, but the mouse was joystick, right? So this is an example, again, of where we want to go, and you can think about those disciplines kind of coming together to make this sort of thing real. That is, robots able to understand enough of what they can do to allocate tasks amongst each other autonomously. Human-machine teaming such that you've got an operator somewhere outside of this environment supervising the team. What kind of information needs to come back? How intelligent do the robots need to be able to ask the right questions when they need help? In the face of things like shifting distributions and some of the stuff that Greg talked about. Okay, so just a little bit of a smattering of some of the work we're doing in this area. So we're thinking, we've kept thinking about this problem and have advanced a lot since the year ago when we showed this at the DRC. So now we've actually got tools in place that allow this particular robot team, Robo-Sally, our humanoid platform, the UAV, the mouse, to autonomously collaborate amongst each other in this increasingly geometric constrained environment. So this map is representative of an indoor environment, and the numbers on the map represent which robot's going to kind of traverse which part of the environment. So this is work that we're doing there. Then you've got autonomous perception. And so what you saw in the video was kind of full motion video feed, relayed to a human operator that could do some thinking. Two reasons why that's not ideal. One, because that's a cognitive workload for the operator. There's a saying in the defense circles is that it takes a village to fly a UAV. So we'd like to invert that equation, right? We'd like to have one human controlling many systems. In order to do that, the system has to go out and do its own perception and do reasoning on those products coming from those sensors to decide what to do. So you've all heard of the progress that deep learning is making with ImageNet, the large data set of images, and the ability of computers to classify objects in static images is almost near to humans, in some cases even exceeding humans on some tasks. What we really want to do is extend this and be able to leverage that in the context of machine processing full motion video, and then also able to reason about things in the environment that it's never seen before. Because even though I can download a deep net from the internet that knows about 200 different object classes, there's more than 200 different object classes in the world that needs to be able to interact with those and say something about it. So we're looking at zero-shot learning. This is an actual result where we presented a deep net with a camera. It doesn't know anything about cameras, but it does know a lot about other objects. In this tree here, it's able to reason semantically about what the object might be, and then maybe be able to tell you something about it or interact with it in a way that doesn't require it to know exactly what it is. And so the interesting thing here is that the reasoning is managing this trade-off between confidence and specificity. So at the top of this hierarchy it's a thing. And it can tell me that with 100% confidence, but it's completely useless, right? And then in this case, it's gone all the way down the hierarchy and gotten it wrong. It thinks it's a bullet. But the impressive thing is that it navigated this hierarchy all the way down to instrument and device correctly. So it can correctly tell me this is an instrument, this is a device. And so what we're doing is we're working to extend algorithms from the academia to really help the machine to manage this kind of trade-off between specificity and confidence in the kinds of scenarios and with the kinds of objects that we care about in this national security context. Okay, and finally, secondly, we talked about smarter machines, better teammates. In this context of better teammates, we think about more intuitive interfaces to navigate that spectrum between command of a machine, I tell you what to do, you figure out how to do it, and control of the machine, which is, at the lowest level, I joystick you and you do something. And the reality is, there's scales you can look up that talk about the level of autonomy of a system. And we sort of reject this notion of a level of autonomy of a system. We think there's going to be a human-machine team performing some task in sort of this fluid exchange between these command and control paradigms. and we're building interfaces to try to navigate that from visual immersive environments using things like Oculus, natural language commands, planning and control. So you remember that map of the indoor environment. We've got tools where the robot can tell me what it thinks the map is. I can draw on the tablet where it ought to go, and then it'll actually plan real trajectories based on the things I've drawn on the tablet. And then the most forward-looking thing that we're doing is looking at brain-computer interfaces. So this is an example. Actually, you can go ahead and play this video. It's an example of a brain-computer interface. This is Jan. She's a paraplegic, and she's using this modular prosthetic limb that we developed for DARPA in conjunction with many other partners on the Revolutionizing Prosthetics program. She's had brain surgery to help us with this experiment. This is several years back. And so what you can see in her head is a cortical implant there. Again, she's paralyzed from the neck down. And you can see she's controlling this robotic arm with her thoughts and feeding herself this chocolate bar. So this is an example, again, of prosthetic control. What we want to push here, if you look at the fighting forces, integrating capabilities like this, we can't ask our soldiers and men and women in uniform to get brain surgery to have this level of control, right? And so where we're pushing this is towards non-invasive brain-computer interfaces with this kind of power. Okay, and then I know I've been talking fast, so maybe we'll have more time for questions. But just to leave you with some thoughts. So what I hope I've conveyed is, our challenge as we think about how to leverage the tools and innovation, I think, is to be thinking about effective human-machine teams and greater machine autonomy in that context to really allow for next-generation capabilities for our critical challenges. That will involve smarter machines, better teammates, trusted autonomy, and the work that we're doing for the government and for our sponsors is right in the middle, trying to put systems together that bring those things together. Some of the policy considerations or just considerations for a forum like this, when we think about the research investment and focus, I think we need a lot more emphasis on, again, effective human-machine teams and research that really bears that out and drives forward in that. I think we need an increased focus on the test and evaluation certification of autonomous systems. When you look at the particular challenges, this is another report that's pretty good. There's the Autonomy Community of Interest for the Department of Defense has put out a report on the challenges of test and evaluation of autonomous systems, which is a really good one. And so we need to be thinking about even novel approaches and novel technologies that can test autonomous systems. Right? Regression testing is not going to get it for a machine that operates with autonomy. And then finally, we need to think about this notion of authority and accountability. If I can trust a machine enough to allow it to make its own decisions sometimes, the hypothesis is that we can get value from that. If I've got a network intrusion, for example, and I actually, we know we have network intrusion agents that monitor for those things. But if I can empower that to actually turn computers off or take whatever action it needs to on a computer clock cycle time without me having to look over its shoulder on human time, think about how many gigabytes of information I've stopped from being exfilled, for example. So we need to think about this problem of delegating critical decisions to machines and what kinds of authority and accountability measures need to be put in place so we can realize that value. So that's what I've got to say here, and I'm happy to take questions.
Do you have a system, or thinking about a system whereby the trusted autonomous machines are reviewed and the decisions are reviewed, and that goes into some kind of feedback loop that develops better decision making and better rules for those machines? Is there a process like that, and how autonomous can that process be?
Yeah, good point. So this is the proverbial black box in the systems, and our position is there should always be this black box to the extent that that's practical. We want to record everything, the decisions the machine makes, the decisions the human makes in interacting with the machine, and be able to, again, enhance the effectiveness of that team using those data. And we've got examples of systems in many different areas where we've done that, these monitoring systems that are on board. That's not always, or that can be a trade-off sometimes, where you've got, say, a really lightweight system. Let's say I want to make a little system that's as small as an insect. Well, could I put a black box on that? I trade between size, weight, and power, and some of these things that are critical, like the black box functionality. So that's a trade space we have to navigate sometimes.
examples you gave were mostly in the physical world. Have you any
examples in the cyber world, working with systems of systems?
Sure. So, yeah. So the physical, the embodied agents make for good videos.
Right.
But we're certainly helping to think about in cyberspace. You know, I gave the example of the intrusion agent that you empower to do things, and there was a cyber grand challenge that DARPA hosted recently, where they had cyber bots fighting each other for control of a system, right? So we're thinking along these lines as well. So we think about intelligent systems. We're thinking about anything from algorithms and software to embodied agents. So we're thinking about that whole spectrum. Yes.
Hi, Samantha Ellinger with GetScoop. I had a question about the robots you're working on with the Department of Energy to decommission nuclear sites. I was curious, how autonomous are you trying to make those? Are you trying to make them so that they're able to also like ask you questions if they don't know how to handle an area, stuff like that? I was curious, like how much artificial intelligence are you trying to kind of put into those systems? Are they just basically like robots that are going to go in and work off of joystick like tasks?
Yeah, it's a good question. So right now, we're among the performers that the DOE is sort of considering. So we're not deep into that task yet. I think it's in a very formative stage. And I think you asked the key, a key question. So I don't know the answer to that question. But the idea here is really, again, the human-machine team. The idea is that you're always going to have a human in command of the system and to some extent controlling the system. And the idea there is that, at least my notion, is that the further you can push to the left with still having the human in control and having the reliability, the better it is, because the decrease in workload, all that. So that's kind of the trade space. You asked one of the key questions that I think we'll be working with DOE and actually many of our other sponsors as well to try to answer. Where is that point that you want to find in that space? All right, well, thank you very much.